Hello, everyone. My name is Dr.E.Purushotham, Professor of Physics, Department of Basic Sciences, School of Sciences and Humanities. Today, I am going to discuss about classification of nanomaterials. It is also known as types of nanomaterials. So, depending on their dimensionality, the nanomaterials are classified into four types: zero dimensional, one dimensional, two dimensional, and three dimensional nanomaterials. So, welcome to today's video lecture that is classification of nanomaterials. Classification: the nanomaterials are classified into four categories based on their dimensions: zero dimensional, one dimensional, two dimensional, and three dimensional nanomaterials. Yes, so try to see here zero dimensional nanomaterials. Nanomaterials with all dimensions in the nanometer range of 1 to 100 nanometers, such as spherical nanoparticles, quantum dots, carbon nanodots, and fullerenes. So, one dimensional also you can see here. We will discuss later after zero dimensional. So, zero dimensional nano materials, when the material is confined to zero dimensions, the charge carriers are confined in all the directions. The charge carriers are confined in all the directions, but there is no movement in charge carriers. There is no free carriers. This type of nanomaterials are known as zero dimensional nanomaterials. For example, quantum dot. So it is clearly written by me, quantum dot. You can see here. So we can also give the graph between energy levels and density of energy states. A typical representation of quantum dot energy versus density of states as shown in this figure. So this is the graphical representation. When the material is confined to zero dimensional or zero dimensions, the charge carriers are confined in all the directions. Thus, there is no free carriers, that is known as zero dimensional nanoparticles. Yes, you see here zero dimensional nanomaterials. Zero dimensional nanomaterials have all dimensions at the nanoscale. Example clearly you can see nanoparticles, quantum dots. The zero dimensional nanoparticles exhibit pronounced quantum confinement leading to discrete energy levels. Their high surface to volume ratio enhances surface activity. Zero dimensional materials show strong optical and electronic tunability. Their small size and surface energy make them suitable for catalysis and drug delivery. Examples include gold nanoparticles, carbon dots, and semiconductor quantum dots also. They are widely used in imaging, sensing, and targeted drug delivery systems. So, high surface energy levels to strong interactions with surrounding environments. So, the zero dimensional nanoparticles gives the photoluminescence properties arise due to the quantum confinement effect. The zero dimensional nanoparticle exhibit size independent band gap tuning vital for optoelectronic devices. You see here, agglomeration is a common challenge due to high surface reactivity. So, functionalization is used to stabilize and tailor uses that surface properties. You can see here, small size enables cellular level biological interactions. So, these are giving magnetic, electronic, and optical behaviors or size tunable related one. So, coming to one dimensional nanoparticles. Nanomaterials with a high length to diameter ratio, such as nanorods, nanotubes, and nanowires. What is one dimensional nanomaterial? You try to see. When the material is confined to one dimensions, the charge carriers are free to move in one direction. One dimensional nanomaterials. When the material is confined to one dimensions, the charge carriers are free to move in one direction. What are the examples you try to see here? Quantum wire, you see, thin film, surface coatings. A typical example for one dimensional confinement is quantum wire as shown here. The graph also we can see between discrete energy levels versus density of energy states. In one-dimensional nanomaterials, grains will be layered in the form of multi-layers such as thin films or surface coating. So coming to these properties. So one-dimensional nanomaterials have one dimension outside the nanoscale like nanowires, nanorods, and nanotubes. So the same image of one dimensional also we can observe here. Their one dimensional nanomaterials aspect ratio supports unique mechanical and electrical properties. Applications also try to see here include field effect transistors, biosensors, and supercapacitors. The one dimensional nanomaterials are used in field effect transistors, biosensors, and supercapacitors. You see here the surface to volume ratio is still high, adding in efficient surface reactions, carbon nanotubes, and titanium dioxide nanorods are common examples of these one dimensional nanomaterials. So, due to their anisotropic nature, is exploited in energy devices and sensors. So you see here properties clearly, one-dimensional nanomaterials. Electron and phonon transport is highly directional due to the one-dimensional structure of these nanomaterials. Surface states also influence conductivity and reactivity in devices for one-dimensional nanomaterials. So carbon nanotubes exhibit exceptional mechanical strength and thermal conductivity. Quantum confinement in radial direction affects band structures also we try to understand here. The functionalized one-dimensional structures improves sensitivity in one-dimensional nanomaterials. Yes, coming to nanomaterials for two-dimensional nanomaterials. So, when the material is confined to two-dimensional nanomaterials, the charge carriers free to move in a plane that is x y direction. So when the material is confined to two dimensions, the charge carriers free to move in a plane. The charge carriers are available, but they are not moving, that is zero dimensional. The charge carriers free to move in one direction, that is one dimensional nanomaterial. The charge carriers free to move in a plane, that is known as two dimensional nanomaterial. Example, quantum well nanotubes. The two dimensional quantum well structure and its discrete energy levels of density of states. This is the structure, this is the discrete energy level we can observe here. In two dimensional materials, grains will be layered, layer over the layer, such as nanotubes. Yes, two dimensional nanomaterials properties we can observe here. Two dimensional nanomaterials have two dimensions in the nanoscale and extend laterally in one dimension. Two-dimensional nanomaterials possess large surface area with atomic level thickness, enabling unique surface phenomena. So quantum, so graphene and transition metals, everything we can see here, two-dimensional nanomaterials. Quantum confinement effect occurs in one dimension, altering optical, electrical properties and also two-dimensional. Their surface is fully exposed, making them highly sensitive and external stimuli. So try to see here simple applications, including flexible electronics, supercapacitors, and gas sensors. The two-dimensional nanomaterials are used in flexible electronics, supercapacitors, and gas sensors. Due to their high mechanical strength and conductivity, support integration in nanoelectronics. So, properties of two-dimensional nanomaterials. The two-dimensional nanomaterials are having high surface area to volume ratio, enables superior absorption and catalytic behavior. So this is co-doped related one we clearly understand here. Their large planar surface allows easy functionalization and hybridization. Two-dimensional nanomaterials exhibit strong anisotropy in transport and optical properties. They are ideal for high-speed transistors, photodetectors, and sensors. Wearable sensors. Three-dimensional nanomaterials. All the charge carriers free to move in all the three XYZ directions, that is three dimensional. Example, precipitates, colloids, example. So you see here the three dimensional confinement structures and its discrete energy levels are shown here. This is the bulk structure, this is energy, discrete energy levels as shown here. All the charge carriers are available, but there is no free to move in three dimensional, that is zero dimensional. Try to understand the zero dimensional and three dimensional nanomaterials. In both, in all the directions, the charge carriers are available, but there is no free charge carriers in zero dimensional nanomaterials, but free to move in all the directions that charge carriers in three dimensional nanomaterials. All the charge carriers free to move in the three dimensions X, Y, Z. Example, precipitates, colloids, example. The three dimensional structure as shown here and discrete energy levels also we are showing here. So, three-dimensional nanomaterials. The three-dimensional nanomaterials consist of nanoscale building blocks forming a bulk structure. So these are the metal oxide related structures. Every structure you can observe here clearly. They integrate nanoscale properties with macroscopic stability and processability. So these three-dimensional examples include nanocubes, nanoflowers, you can see in the figure, nanoporous flameworks, and aerogels. Surface and internal nanostructures of these three-dimensional nanomaterials, these are used in many devices. 3D structures are used in catalysis, tissues, and battery electrodes. Their design flexibility enables very simple architectures for energy applications. So coming to here, the top-down and bottom-up approaches. There are plenty of methods to synthesis nanomaterials. These methods are grouped into two categories, namely top-down and bottom-up techniques. Top-down approaches refers to a subtractive process in which a bulk starting materials is divided into smaller ones of nano size. Bottom-up approaches refers to an additional process that starts with precursor atoms or molecules which combine for form nano-sized structures. So top-down examples you can see ball milling or mechanical crushing method, lithography, attaching, erosion. So bottom of related sol gel method, CVD chemical vapor deposition, PVD physical vapor deposition, ED electrochemical deposition, ALD atomic layer deposition, hydrothermal methods. So two-dimensional, you see here, nanomaterials with two dimensions in the nanoscale, such as graphene, nanosheets, nanofilms, and thin films. Three-dimensional, nanomaterials made up of zero-dimensional, one-dimensional, or two-dimensional nanostructures, such as nanoprisms, nanoflowers, bulk powders, and bundles of nanowires. So zero-dimensional nanomaterials properties. You can see here. So property detailed explanation. Quantum confinement of zero dimensional nanomaterials. So electrons are confined in all three dimensions, creating discrete energy levels and causing size dependent optical and electronic behavior. This is the property of quantum confinement effect. High surface area to volume ratio. So the number of atoms lie on the surface, increasing reactivity and enhancing interactions with surrounding molecules. So it gives the different properties to zero dimensional nanomaterials. The zero dimensional nanomaterial size dependent optical properties. So due to the absorption, the optical absorption and emission shift with the size. The size is the changing of zero dimensional nanoparticles gives the optical absorption and emission. Smaller particles emit higher energy light and vice versa. Enhanced catalysis, catalytic activity. So large surface area and active sites make nanoparticles excellent catalysts with faster reaction rates for zero dimensional nanomaterials. So discrete energy levels effect for zero dimensional nanomaterials. You see here lack of continuous energy bands. Electrons occupy quantized levels similar to artificial atoms. Then the properties are changing. Strong photoluminescence property. So it gives the efficient light emission upon excitation with tunable color useful for light emitting diodes and bioimaging related one. High chemical reactivity. So unstructured surface atoms and high surface energy makes nanoparticles high reactive related for zero dimensional. So the property tunable magnetic behavior. The magnetic properties such as super paramagnetism can be controlled by adjusting the particle size. So what are the applications of zero dimensional nanoparticles? Zero dimensional nanoparticles are used in bioimaging and medical diagnostics. First one. You see here, quantum dots and other zero dimensional particles emit bright, size tunable fluorescence, making them ideal for labeling cells, tracking biological process, and improving medical imaging accuracy. The zero dimensional nanoparticles are used in drug delivery systems. You see here nanoparticles such as liposomes and polymer nanoparticles can carry drugs directly to targeted tissues, increasing therapeutic efficiency and reducing side effects. Their small size enables easy entry into the cells. So, zero dimensional nanoparticles are used in photovoltaic and optoelectronic devices. Zero dimensional materials enhance light absorption and charge separation in solar cells. Their tunable optical properties make them suitable for light emitting diodes, display technologies, and photodetectors. Zero dimensional nanomaterials are used in catalysis and chemical sensors. Due to their high surface area and reactive surface atom, zero dimensional nanoparticles serves as excellent catalysts for chemical reactions and are used in gas, humidity, and biosensors for fast and sensitive detection. So coming to quantum computing components. The zero dimensional nanomaterials are used in quantum computing components. Quantum dots behave like artificial atoms with discrete energy levels. They are used in qubits, single electron transistors, and other emerging quantum devices. So, coming to one dimensional nanomaterials properties. So, you see here property high aspect ratio. So, you see here length is much larger than diameter, it improving mechanical strength and directional transport. The one-dimensional nanoparticles property, anisotropic properties. So due to this, their anisotropic property, these are in electrical, optical, and thermal properties vary with direction due to elonged shape. Another one, efficient charge transport property. You see here simply electrons move with minimal scattering along the length, enhancing conductivity. So, due to the large surface area of one dimensional nanomaterials, this property, the small diameter provides high surface area, improving adsorption and catalytic behavior. Quantum confinement effect property. It carries or carriers are confined radially but move freely along the length, causing size dependent property. High mechanical strength property of one dimensional nanomaterials, that is, nanotubes, nanowires, show excellent tensile strength due to strong covalent bonding. Tunable optical properties. So, the properties optical absorption, emission change with diameter, length, and structure. So, enhanced thermal conductivity for one dimensional nanomaterials conduct heat efficiently along the axis, useful for thermal management. So, these are the properties of one dimensional nanomaterials. Coming to one dimensional nanomaterials applications. Yes, application nano electronics and transistors. One dimensional nanomaterials are used in nanoelectronics and transistors. One dimensional nanowires and nanotubes provide efficient, so it making them ideal for high performance transistors, interconnects, and next generation electronic circuits. Low scattering paths for electron transport, making them ideal for high performance transistors. The one dimensional nanomaterials are used in sensors, that is, chemical, biological, gas, etc. Due to the one dimensional nanomaterials' large surface area and high aspect ratio, enable fast and sensitive detection. You try to see here the small changes in the surroundings environment also causes measurable changes in electrical and optical signals. One dimensional nanomaterials are used in energy storage devices. The devices are batteries and supercapacitors. One dimensional nanostructures offer short ion diffusion paths and large surface contact, improving charge storage, cycling stability, and conductivity in lithium ion batteries and supercapacitors. So, one dimensional nanomaterials are used in photonic and optoelectronic devices. So, nanorods and nanowires exhibit tunable optical properties and efficient light guiding. They are used in light emitting diodes, lasers, photodetectors, and optical wave guides. One dimensional nanomaterials are used in reinforcement in composite materials. Carbon nanotubes and nanofibers greatly enhance mechanical strength, flexibility, and thermal conductivity of the polymers and metals, creating lightweight and strong composite materials. Coming to two-dimensional nanomaterials properties. The two-dimensional nanomaterials properties, we are going to study high surface area, strong in plane bonding, weak interlayer forces, quantum confinement in thickness, direction, high charge carriers, mobility, anisotropic behavior. Yes, the property high surface area. Because two-dimensional materials are only one or few atoms thick, almost all atoms are exposed on the surface. Because of these are freely move in two-dimensional. This gives them an exceptional high surface to volume ratio, useful in catalysis, sensing, and energy storage. Strong in plane bonding. Atoms within the you see here within the layer are bounded by strong covalent bonds. It provides mechanical strength, thermal stability, and robustness within the plane along x direction or y direction. Examples include graphenes, strong carbon-carbon bonds. Coming to weak interlayer forces. You see here, stocked layers are held together by weak van der Waal forces. This allows easy exfoliation into single or few layer sheets and enables tunable stacking for tailored properties. Another property, quantum confinement in thickness direction. You see here, electrons are free to move in the plane but confined to the out of plane due to the thickness, out of the plane direction. This confinement leads to tunable electronic, optical, and magnetic behavior as the number of layers changes. Due to the changing of number of layers in the plane, we can observe the different tunable electronic, optical, and magnetic behavior of two-dimensional nanomaterials. So high charge carriers mobility. You see here, two-dimensional materials allows fast, low resistance movement of electrons within the plane. So graphene, for example, shows extremely high carrier mobility, beneficial for high speed electrons and photodetectors. Coming to anisotropic behavior. Properties like electrical conductivity, so magnetism related, and optical absorption are different in plane versus out of plane. This type of anisotropy is exploited in sensors, transistors, and layered heterostructures. So, coming to two-dimensional nanomaterials applications. Two-dimensional nanomaterials are we can observe in flexible and transparent electronics. Two-dimensional nanomaterials like graphene are extremely thin, flexible, and highly conductive. They are used in bendable displays, wearable sensors, transparent electrodes, and next generation touch screens. Energy storage devices, that is batteries and supercapacitors. Due to the two-dimensional nanomaterials large surface area and fast in plane charge transport, enhance ion storage and conductivity. So the graphene oxide significantly improve the performance of lithium ion batteries and supercapacitors. So two-dimensional nanomaterials, high performance transistors. These are used in transistors. Two-dimensional nanomaterials such as MOS2 offer tunable band gaps and very high carrier mobility, making them excellent candidates for ultra small, low power field effect transistors, that is FETs. So catalysis and electrochemical reactions. The two-dimensional nanomaterials are used in catalysis and electrochemical reactions due to the nano two-dimensional nanomaterials, large surface area, abundant activity sites, and tunable thickness. Two-dimensional materials are widely used in water splitting, carbon dioxide reduction, hydrogen evaluation, and fuel cell catalysis. The two-dimensional nanomaterials are used in sensors, that is gas sensors, chemical biosensors. Due to the two-dimensional nanomaterials atomic scale thickness enables detection at extremely low concentrations. Even small amount of absorbed molecules cause large changes in electrical optical properties, enabling ultra-sensitive gas and biosensing. Biosensing. Coming to three-dimensional nanomaterials properties. Yes, you can observe here high density of grain boundaries. Three-dimensional nanomaterials consist of many nano-sized grains packed together. This creates a huge number of grain boundaries, which enhance mechanical strength, increase diffusion rate, and affect electrical thermal conductivity. So another property, enhanced mechanical strength. Due to nanometer-sized grains, these materials often exhibit high hardness and strength, Hall pitch effect, it is called. The reduction in grain size restricts dislocation movement, making the material mechanically stronger. So, improved thermal stability, another property. So, number of three-dimensional nanomaterials withstand high temperatures because their compact structure and strong interface bonding reduce thermal expansion and improve heat resistance. Another one, tolerable property. Three-dimensional nanomaterials such as nanoporous metals and aerogels allow controlled pore size and distribution. This porosity enhance absorption, filtration, catalytic reactions, and energy storage properties. Coming to enhanced catalytic performance. The presence of large material surface area, multiple active sites, and interconnected networks of pores significantly boost catalytic efficiency in chemical and electrochemical reactions. So, high electrical conductivity. Three-dimensional nanomaterials, due to their composed of conductivity nanoparticles, example metal nanostructures, three-dimensional nanomaterials show excellent electron transport through interconnected networks, useful for electrodes and sensors. So, coming to three-dimensional nanomaterials applications. Yes, the three-dimensional nanomaterials are used in energy storage devices, that is, batteries and also supercapacitors. Three-dimensional nanostructures provide interconnected channels and high porosity, allowing faster ion transport higher charge storage. So coming to second one, catalysis and chemical reaction. The three-dimensional nanomaterials are used in catalysis and chemical reactions. Large surface area and abundant catalytic sites enhance reactions rates. Three-dimensional materials like MOFs, porous carbon, and metal oxides are used in hydrogen evaluation, carbon dioxide reduction, fuel cells, and pollutant degradation. So coming to next one, this is water treatment and environmental remediation. Three-dimensional nanomaterials are used in water treatment. So porous three-dimensional materials absorbs heavy metals, dyes, pollutant, and oil efficiently. They enable filtration, absorption, and photocatalytic breakdown of containments in water and air. So, coming to biomedical and healthcare applications. The three-dimensional nanomaterials are used in biomedical and healthcare applications. That is, three-dimensional nanostructures like scaffolds and aerogels support cell growth, enable controlled drug delivery, bone repair, antibacterial coating, and biosensitizing due to the high biocomposites. So, coming to another one, electronics and sensors. Three-dimensional nanomaterials are used in electronics and sensors. So, coming to another property, energy harvesting, that is solar, thermoelectricity, piezoelectricity. The three-dimensional nanomaterials are used in energy harvesting, that is, these are used in solar cells, thermoelectricity, electric effect, piezoelectric effect. Three-dimensional nanomaterials enhance light absorption, electron transport, and thermal management, improving solar cells, thermoelectric devices, piezoelectric generators, and photocatalytic hydrogen production. The three-dimensional nanomaterials are used in this. Piezoelectric, nanogenerators, and photocatalytic hydrogen production. Three-dimensional nanomaterials are used in mechanical and structural applications. 3D aerogels and carbon nanotubes, spawns provide ultra lightweight. These are used in optoelectronics and photonics. So, three-dimensional photonics crystals and nanostructures LEDs control light propagation, enabling advanced displays, optical sensors, lasers, and photonic devices. So, three-dimensional nanomaterials are used in lasers, optical sensors, so advanced displays, photonic devices. So, application in environmental sensing and monitoring. High surface area enhance absorption of gases and chemicals, making three-dimensional materials highly sensitive for detecting toxic gases, humidity, temperature, and pressure changes. So, coming to construction and civil engineering. So, the three-dimensional nanomaterials are used in construction related and also civil engineering. The three-dimensional nanostructured additives strengthen cement and concrete, improve durability, create self-cleaning surface, and provide thermal insulating materials. So try to understand the summary of today's video. We given depending on their dimensionality. The nanomaterials are classified into four types. That is zero dimensional, one dimensional, two dimensional, and three dimensional. The charge carriers are available in all the directions, but there is no free charge carriers. That is zero dimensional nanomaterials we studied in this video. This is the summary. So the free charge carriers are moving in only one direction, that is one dimensional nanomaterials. If the charge carriers are free to move in a plane, that is two dimensional nanomaterials. If the charge carriers are free to move in a three dimensional, that is called space, that is xyz direction, that is three dimensional nanomaterials. So in this video, we studied about zero dimensional, one dimensional, two dimensional, and three dimensional nanomaterials. And we discussed clearly with the figures and images the properties and applications of zero dimensional, one dimensional, two dimensional, and three dimensional nanomaterials. And also, we discussed clearly examples of this classification of nanomaterials. Thank you so much. Thank you for observing this video. Thank you. Thank you so much.